Huh. Well, that didn't work out very well, now did it? Alright, let's get going here. Chapter 6, first part, inference for categorical data. This is going to be about proportion tests only. So a proportion test, a lot of this is the same structure as hypothesis testing for two means or for one mean. So you can have a test for one proportion, which is like a single sample t-test or z-test, or a test for two proportions, which is like a two-sample t-test or z-test. And we're only going to talk about the independent samples type case here instead of paired samples. So it's just a z-test, and it's a test for proportions instead of means. And I'll explain that in just a minute. You have one sample versions of this test, paired samples versions of this test, or independent samples versions. We're only going to look at one sample and independent samples. The standard easier is, it says it's a lot easier. It's a little easier to calculate than in the t-test, and the hypothesis test procedures are otherwise pretty much the same. You just follow the hypothesis test, but you plug in proportions instead of means, and plug in the formula for a standard error instead of the formula that you previously had for standard error. So when do you use this? This is the hard part. It's the most difficult thing here is figuring out when you're supposed to apply this situation. And that is when you have counts or binary data for a group of people for some condition for each individual. You can call it counts, you can call it binary data, you can call it dichotomous data, and you want to look at the distribution of those counts in one group of individuals or two groups of individuals. So let me just show you an example here. Now, in this textbook we use a z-test. Some textbooks use a t-test for this. The outcome is extremely similar in most cases. So if you have a t-test between two groups, this is what you have. Two groups of observations. Let's say there are two groups of individuals. And I'm putting these little scale things here to show in this symbolic representation that each person or each case or each individual in the study could have a value on some variable. So it's a variable that is numeric and it has multiple possible values ranging from a low value down here up to a high value here. Like it could be the person's body temperature, it could be their level of racism as measured by some scale or something like that. So let's say there's this person here and their value is, it looks like we have a 0, 1, 2, 3, 4, like a 5-point scale from 0, or 6-point scale from 0 to 5. This person has a 3, and this person has like a 1.5, and this person has a 0, 1, 2, 3, like a 3.7, and this one person has like a 1.8, etc. And this has a 1. So you would calculate the mean of all those people's values, and that's the mean of group 1. This is what we've been doing so far. This is not new. And then in group 2, everybody has a value, and you calculate a mean for group 2, and you do a t-test for independent samples to determine whether the differences between those means that we see in these two little samples seem like they're likely to be reflecting differences between means in the actual populations. So same process for proportion tests, it's just that we're looking at proportions. Sometimes you say that there are just counts in each group, or sometimes you could also conceptualize this as binary or dichotomous data, meaning each person can only have one of two possible values. Anything that's just two possible values, that each individual can only have one of two possible outcomes. That's binary or dichotomous variables, and when you clump them together in groups, then you're just basically counting things. So I'll show you what that means. Let's say it's, I don't know, are you Democrat or Republican, and maybe those are the only choices. And this person's a Democrat, Republican, Republican, Democrat, Republican. So I'm just using this little symbol that there's two possible checkboxes, and you have to check one, but not both. So you could also imagine this is male or female. This person's male, female, female, male, female. Or you could imagine that it's a person got a GPA of a C or greater or not. So this person has a C average or greater, this one doesn't, this one doesn't, this one does, this one doesn't. So you see how anything that you split or that naturally comes in a version that only has two values can become this binary dichotomous type variable. And you could think of it as a binary or dichotomous variable, or you can just think of it as counting one point on that scale. It's a scale with two values, this one and this one. Sometimes people turn it automatically into 0 and 1 because we do that when we're coding sometimes if you have to force numbers. 0 and 1 are nice, but you can use 1 and 2, or 3 and 279, or M and F, or whatever you want, as long as there's only two possibilities. But if you count the number of times one of those possibilities occurs in each group, then this becomes count data. Same thing. Binary data, count data, same thing. So there's the number of people. Let's say this is male and female. You have 2 males. You don't have to know the number of females, right? You just have to know there's 2 males and the number of people and the fact that there can only be 2 possibilities. And then 2 males means 3 females. And then you look in the other group and you count that number. And so then you get a proportion. So you could count the number, but as long as you know the number and the number of people checking, this box off, like one number of people with one alternative on this binary variable, and then you know the number of people in each group, you can get the proportion. So this is why we're talking about a proportion test. Proportion or percentage. Proportions are what we use for the math, but we think of them as percentages quite frequently. So in this case, 40% of the people here are, I don't know, let's say males. Let's say the top box means male. And here, 80% are male. So 4 out of 5, 80%. Or maybe they're dentists, and this is the 4 out of 5 dentists that they always talk about. Anyway, proportions. So you'll want to see the proportion of people in one group versus the other. Now, it doesn't matter whether you choose this, like one alternative, so let's say this is male or female. It doesn't matter whether you look at the proportions of males or the proportions of females. If it's proportions of females, then you'd say 60% female in this group and 20% female in this group. As long as you're consistent and you're talking about the same thing in both groups, then the test will result exactly the same. So you just pick one of those alternatives, and sometimes it's obvious which one you should pick. So the z-test for proportion from a single sample, now we did a 2-sample thing here, so just cover up one side of your screen, and that's like a 1-sample situation. So proportion from a single sample, it's basically to see whether the split is different from 50-50. So the null alternative proportion is usually 0.5, so you take the observed proportion minus the null observed proportion. So this is often 0.5. So this is the difference from 0.55. And you divide it by the standard error of the proportion. And then you have a z, the end. You're done. It's the same as a single sample z-test. The standard error of the proportion, the only thing you need to know is the proportion of the thing you're counting in the group. And then you do that, and then 1 minus the same thing, and divide by n. So proportion and n is all you need for the standard error. And it turns into a z that's normally distributed. And the confidence interval, you do the same thing. You just figure out the z, which is probably 1.96 that you would need for your confidence interval. And you do plus or minus, you do your proportion, plus or minus z times your standard error of your proportion. So this is the same as a single sample z-test. You just need to apply this formula here, and you get a single sample proportion test turned into a z-test. Once we've turned it into a z-test, we're home. We know how to do z's. Once you have, this is a z observed for proportions. You just look up your z critical for proportions, but you don't even need to look it up. Like for for a two-tailed 0.05, it's going to be 1.96, etc. 1.65 for two-tailed, 0.10, or one-tailed 0.05, etc. So, just a simple z situation. So, for instance, you could say my 95% confidence interval is the observed proportion times 1.96, or plus or minus 1.96 times whatever the standard error was for a 90% or 95% confidence interval. So the difference between two independent proportions is really similar. It's just a slightly more complicated standard error formula, really. So you take the difference between the two proportions, proportion of whatever it is from group 1, like say what proportion of males in group 1, what proportion of males in group 2, you divide it by the standard error of the difference between proportions. And of course there's a formula. The formula just requires you to know the proportion in group 1 and the n in group 1, and the proportion in group 2 and the n in group 2. These n's don't have to be the same, by the way. They can be different. Otherwise, it's the same. You just take this difference. Now, this implies this difference minus the null hypothesized difference between the two proportions, but once we have two groups, it's almost always that null hypothesis difference between proportions is going to be 0. In other words, the null hypothesis is almost always that the proportions are the same in the two groups, therefore the difference between them will be 0, so we don't even put the null hypothesis part in this formula. We just put the difference between the two proportions, because the null hypothesis part is 0, and it just disappears. So that's the formula. And then the confidence interval is the same. You just take this standard error, and this observed difference between proportions. So you take the difference between proportions plus or minus whatever your z critical is for confidence interval, like 1.96 or 2.58 or something, times this standard error that you calculated. So it's the same process as a z-test or a t-test for two samples. The difference between two paired or dependent proportions, it exists. We're not going to do it. If you ever need to do it, you probably figured out enough now that you can just look it up in a textbook and figure out how to do it. And the confidence interval, there's a confidence interval, and it will follow almost exactly the same formula as confidence intervals for everything else. It'll be whatever the difference is that you find in your sample, plus or minus the standard error of that difference times the z, like 1.96. So the hypothesis testing procedure looks the same. You state your null and your alternative hypotheses. For a two-sample proportion test, the null is almost always that the proportions are equal. The proportion of whatever it is in this group is the same as the proportion of that same thing in the second group. The alternative is either that the proportion is greater in one group or less than another group, or just not the same. So you can have one- and two-tailed proportion hypotheses. You draw a diagram. It's just a normal distribution. And the middle of that diagram is going to be labeled with the null hypothesis proportion. So 0, or null hypothesis value. So for two sample proportion tests, the middle will be 0 because the difference between the proportions in the two groups is hypothesized to be 0 under the null hypothesis almost all the time for a two sample test. So you can just plug in proportion wherever it says mean, and suddenly this is like a t-test for two groups, except it's z, so it's a little simpler. So you find your z critical and you state your rejection rule, like if my z observed is greater than this value, then I'll reject the null hypothesis. You calculate z observed using the formulas we've seen before, using the proportions and the standard error of the proportion. And then you compare to z critical and to state your decision about the null hypothesis. You state your conclusion in terms of the variables in the research question. As we always do, you're done. And that's it. Proportion tests. They're easy peasy, right? So here's some examples. So we're not going to work through all these examples, but this is the way proportion tests are phrased frequently. This is the kind of setup you'll see. So is the rate of complaints against police officers greater than 10% of all incidents that police officers respond to? Try and think about this and get yourself to the point where you can look at this and say, this is a proportion test. So what this is a single sample proportion. So the null hypothesis is the proportion should be 0.10, 10%. And you're going to collect data and you're going to say, what is the actual proportion? You're going to take the number of complaints against police officers, divide it by the number of total incidents that police officers responded to, and that proportion will be different from 10% to some extent. But then you're going to do a proportion test for a single proportion and determine whether it's more different than you would expect. The null hypothesis is that it's 10%, and it's going to be a one-sample or a one-tailed test because you're saying greater than 10%. So you can run that if you had the data. You could say which school has a higher turnout for baseball games. That implies a percentage of school 1's student body versus the percentage of school 2's student body. So you look at the percentage of students in school 1 who show up for baseball games and the percentage of students in school 2 who show up for baseball games, and you compare those percentages using a two-sample proportion test. You'd convert the percentages to proportions or else the math doesn't work. Did more people pass my class this year or last year? This is a two-tailed test because it doesn't say I hypothesize it's more this year or it's more last year. It just says, is there a difference, and if so, what direction does it go in? Thinking of what the population is a little weird for this. I could probably come up with it, but this is a bit of an odd population situation. What am I sampling here? So I could say passed my class under method A or method B of teaching. That might make more sense. So you take the percentage under both conditions and you compare those percentages. The percentages is just the number of people passing versus the total number of people in the group. Did more students complete my survey for homework 3 or my survey for homework 4? The same thing. What percentage of Americans go to college now versus in 1950? You'd have to have some sample of Americans who went to college now and some sample of Americans in 1950. So in R, this is actually, it's fairly easy to do. There's a prop test function that's in base R. Base R meaning you don't have to download any special packages, just crank up R and it's there. This might exist in R Commander. I should probably check that. Here, let's find out. In base R, you have to create a table. So for one sample, you need to create a frequency table. So for instance, sex in the support data set, male or female. So let's go over to R here. Do I have anything embarrassing open? I always wonder. Let's not use RStudio because most of you don't use that and it's kind of confusing looking. Well, not RStudio, RCommander. So let's crank up RCommander. I've already loaded this data set into the workspace, so I'm just going to select it, the support study. So statistics, proportions, how nice, single sample proportion test. How sweet is that? Sex. That was easy. There we go. We're done. It did a chi-square test for proportions. We're not going to do that if we do things by hand. RCommander does it. The OpenIntro people kind of have objections, but you're going to probably get the same result no matter which way you do it. The p-value is very, very, very small. So the actual proportion of females is 71%. So it's female up here and male here. And the proportion of females is 71%. So, ta-da, the end. We're done. Yes, there is absolutely a statistically significant difference between the percentage of females and the percentage of males in this study. So, going back here, we can do this in base R as well. Base R is really easy. You can do, and then you can do the proportion test that the people in the textbook really want you to do. So, I already loaded the support data set there. And I can look and see this is called sex. So you can't just do, well, let's try. Maybe you can do proportion test. Can you do that? No, you can't. Now that's a weird error, but what it's really telling you, if you look at the help page for proportion test, it needs a table. So we'd say like table, I'll create an object called table. Is table support $sex. Now if I look at table, now I have a frequency table. The proportion test wants a frequency table. So prop.test table. There we go. It gives me exactly the same result. It uses the chi-squared value, etc. So there's no real advantage to doing this in a base in just regular R versus RCommander, I suppose. So use RCommander by all means. So to graph it, you can use a bar chart or maybe even a pie chart. I'm not going to go through that. It's not too difficult to do. For two independent samples, you need a frequency table. And it gets fussy. You need a two-way frequency table or contingency table. It must be organized with successes in column 1 and failures in column 2. It doesn't matter how you define successes and failures. But the groups need to be in rows, and the condition that you're looking at, you know, the yes, no, the this, that, needs to be in the columns. And it kind of doesn't matter which is which, but for interpretation it helps a little if you arrange it the way you want. And that gets a little fussy in R, arranging your data that way. So it wants a table like this. Group 1, Group 2. Now if you just define success as female, failure as male, and these terms are just terms that people sometimes use in the research literature, and I think they're talking about back in the old days when so many of the examples included like flipping a coin or something, and you'd say success was heads and failure was tails because you won the bet or you lost the bet. The language has stuck with us, and so you'll see that in the R documentation frequently statisticians use this term, success and failure. So you have frequency here, frequency like the counts here, 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 and here. So you need a table like this. So for instance, whether you're born in the U.S. Versus no parent college degree, yes or no. So you could arrange your data like this. Born in the U.S., not born in the U.S. No degree. Neither of your parents have a 4-year degree. Some of your parents, at least one of your parents has a 4-year degree. You could arrange the table that way. Now you could do this in R. It's a little fussy, but you can get it done. But I believe you can do this in RCommander too. So let's look at our commander. Statistics, proportions, two-sample proportion test. So group 1, the groups are whether you're born in the I created a new variable. You won't have this in your data set, but whether you're born in the United States yourself or not. And then the response, I didn't code that other variable correctly. So hang on. All right, I fixed it for my demonstration-y purposes here. So looking in our commander here, let's see here, statistics, proportions, two-sample proportions test. All right, so groups, born.self is were you born in the U.S. or outside the U.S., and the response variable will be mother, father, 4-year degree. There we go. And we have some results looking at us in the face here. So, were you born in the U.S.? Yes, no, U.S. or other. And then mother, father, 4-year degree has two options, neither and one or more. So neither of your parents has a 4-year degree, and one or more of your parents has a 4-year degree. Now this created row percents. So this shows you not just the frequencies, but it shows you the percentages in each row. So for people born in the U.S., about 1/4 of them have neither parent with a 4-year degree, and 2/3, 3/4 of them have at least one parent. People born outside the U.S., like 41% have neither parent, and like 59%, which is a little lower, have one or more parent with a 4-year degree. So is this split difference, like the 27-73 split versus the 41-59 split, are those different proportion splits for whether your parents have a degree or not? Well, let's find out. Yes, they are. The p-value is 0.01. So as long as our p was, or our alpha was 0.05, then yeah, there is a significant difference. And it gives you these proportions right here. Proportion 1, 0.27. Notice that's just the neither. R is just going to pick one of them. So in group 1, essentially in the U.S. born group, 27.5% are first-generation college students in the sense that no one in their family actually has a degree. Now, this variable doesn't say did you ever go to college. It just says do you have a 4-year degree. And in group 2, only 41%, quite a bit bigger. So that difference is statistically significant. There are more people, or there's a greater proportion of people who were born outside the U.S. whose parents do not have a 4-year degree than people who were born inside the U.S. Interesting data. How nifty. Now for graphing this, we would want to use a stacked bar chart, which is either kind of annoying or it requires extra packages. And you can't do that in R Commander. You can get an ugly version very easily without doing anything fancy. So you can, here, let me look at my little text here. I created a table. I created a table of support, born self variable, and the support data, mother, father have a 4-year degree variable. And so if I do a bar chart, just like proportion tests, you have to do it on a table. You don't do it just on the variables in the data set. It makes things a little more confusing. But bar plot of table. There we go. We have a bar plot. Now this is confusing. It gave me the columns of neither and one or more. Like this is which parents were born, or which people were born inside the U.S. based on whether your parents, neither of them had a 4-year degree. This isn't how we were conceptualizing things. So we can use this function called T. So table, let's look at table. There we go. Now T means transpose. So now we've transposed the table. So it didn't give me the stacked bar chart the way I wanted it, just using the table. I could go back and reverse these, and I could put this first and this second, or I can just do bar plot not of table but of the transpose of table. There we go. Yeah, this is making more sense here. So this is people born inside the U.S. and well, it would be nice if there were a legend. These are people whose parents do not have 4-year degrees, and these are people whose parents, at least one parent has a 4-year degree. And this is the same thing for people born outside the U.S. Now, you can get something a little bit prettier with a mosaic plot. So using that table again, we just use the function mosaic plot, which we did in the very first part of class. Mosaic plot table. There, it's beautiful. Now you can add X label and Y label. You can add colors if you want and make it pretty. Col is usually the colors, equals C, let's say red, blue. There. Now it's beautiful. So this shows you by areas proportions of people in each group. So this is people born in the US, this is people born outside the US, and these red are the first generation college students, the people whose parents, neither one of them, have a 4-year degree. You can see there's a larger percentage over here, but you also see that this group is smaller than this group. Anyway, it's kind of handy. So I think I'm going to stop now, assuming that worked, and try and upload this.